The goal of this video is to help everyone understand some basic concepts related to summation notation. And so when I talk about summation notation, I'm talking about this Greek symbol sigma, which is often used in mathematics to represent a sum. And in fact, we use this symbol sigma to say that we're adding up contributions when we defined our definite integral. And what I want to do in this video is talk about a particular representation of sums where I have actual indexes where I'm counting over a sequence. So the first thing we want to talk about is we want to talk about what it means to be a sequence. And a sequence is it's a special kind of function. So for example, a traditional function, I might say f of x equals 2x plus 1, and it's understood here that the domain of this function is any real number. So for example, I could talk about finding the value of the function of 3, or the value of the function at a half. So that when I talk about the value of the function at 3, it's 2 times 3 plus 1, which gives me an answer 7. And the function value at a half, when the half is the input, it's 2 times a half plus 1, which gives me a value of 2. But when I talk about a sequence, my domain consists only of integers. And so when I'm talking about my sequence, U subscript n is my index, and my domain consists only of integers. So if I'm talking about my sequence, I might talk about U with an input of 3. So here my index is 3. That's 2 times 3 plus 1, just like a function. But U with a subscript of a half does not make sense, so this is not defined, because that's not an integer. So a sequence is just like a function. There's a little bit of difference in the notation. I use a subscript instead of the parentheses, but otherwise it's the same. So on the previous slide we identified that U subscript 3, which was 2 times 3 plus 1, gave me a value of 7, and I can also find the subscript negative 2. My index is negative 2 plus 1, which gives me a value of negative 3. And when I have a formula like 2n, I think of this like a composition. Using parentheses notation, I would have an input of 2n, so that it's 2 times the input, which is 2n, plus 1, for a grand total of 4n plus 1. And so sequences can have compositions, just like a function can have compositions. Now if I thought about what this sequence was, the idea of a sequence is I have this n value and I have my U sub n. The basic idea is that I'm creating a sequence that counts. So negative 2, negative 1, 0, 1, 2. We found U subscript negative 2. And if I did negative 1, I get negative 1. And so I get this sequence so that I get a relationship between my index and the value of the sequence. And this sequence would go on forever. Now the second example on this slide says I'm given a pattern, and so I want to find a formula for my x of k. Now it tells me that my index starts at 1, so as I'm thinking about this, the first value comes from 1, the second value comes from 2, from 3, from 4, and on and on. In order to find a formula for my sequence, I'm looking for a function that sends 1 to 5. So let's create a function here. N U sub n. 1 goes to 5, 2 goes to 8, 3 goes to 11, 4 goes to 14. And if you look at the sequence, you can see what I'm doing is I'm just adding 3 some repeated number of times. And because I'm adding the same number, this behaves like a line. This behaves like a line with slope 3. So if I were to think about this in the language of a function, my line is the slope times x minus some x value plus b. I'm going to do the same thing for my sequence, where u sub n is my slope, 3, times my independent variable is my index, and then I'm going to pick the first point. I'm going to pick this first point in my pattern. And so what I get is I get a formula that my sequence is 3n minus 3 plus 5 gives me plus 2. And if I look at the pattern, if I plug 1, I get 3 times 1 plus 2 is 5. If I plug 2n, 3 times 2 is 6 plus 2 is 8. If I put 3 in, I get 3 times 3, that's 9, plus 2 equals 11. And so this formula creates the pattern that's described by this sequence. So it behaves just like a regular function. The notation's all that's different. This third slide wants to help you notice that there are 3 main points on a summation notation you need to pay attention to. There is a starting point, which is where I'm going to declare an index variable and a starting value. So let's create a little example here at the bottom. I'm going to have a summation where I start at 3. There's next an ending index. So this tells me where I'm going to end. So if I look at this, I might put a 7 up there. So 7. And the third point, or the third object that I have, is the sequence that I'm actually going to sum. And so here I typically have a formula involving my sequence index. So n is my index, so I might have a formula like 2n plus 1. Okay, so as I look at this, the 3 parts, I declare my index variable n, I say I start at 3, and I'm going to go until my index equals 7. So I look at my sequence, and I'm going to think about my sequence, index n, formula, and I'm interested in the values 3, 4, 5, 6, and 7. And I'm going to use my formula where I do 2n plus 1. So 2 times 3 is 6 plus 1 is 7. 2 times 4, that's 8 plus 1, is 9. So what we can see is I'm counting by 2. So I'll get 11, 13, and 15. Now that I have my sequence for my index starting at n equals 3 and going to n equals 7, I'm going to add up these numbers, 7 plus 9 plus 11 plus 13 plus 15. So the answer, the answer, 7 plus 9 plus 11 plus 13 plus 15, which gives me a value of 55. So that summation notation allows me to identify the index, my starting index value, the ending index value, so I go from 3 to 7 on the index, and the sequence tells me the number formula of what the values are I'm going to actually add. Now we get to practice. I have 3 summations. Each of them has a different index, a different starting and ending value, and a different formula. So I suggest you pause right here, see if you can find these values, and then start up and check your work. Okay, for our first summation, we're going to use the formula 2n minus 5, and we're going to use our index n that counts from 3 to 7. So I get 2 times 3 minus 5 plus 2 times 4 minus 5 plus 2 times 5 minus 5 plus 2 times 6 minus 5 plus 2 times 7 minus 5. So I've used my index, counting from 3, 4, 5, 6, and 7, using the formula 2n minus 5 on each of those index values, and that gives me the numbers that I'm going to add up. And so I calculate those values and get 1, 3, 5, 7, and 9. I add them all up and get a total of 25. That's the first sum. For our second summation, I have an index of k. I'm going to count starting with the value 0, ending at the value 5, where I use the formula sine of k pi over 6, and there's my index k. So I'll write down each of the values, and so I get my index 0, 1, 2, 3, 4, 5, using my formula sine 0 pi 6, 1 pi 6, sine of 2 pi 6, sine of 3 pi over 6, sine of 4 pi over 6, sine of 5 pi over 6. And now what I need to do is I need to find all those values, and I'll do that by thinking about my unit circle. So my unit circle, pi over 6 is 30 degrees. And so in terms of pi over 6, this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and 5 pi over 6. So as I think about what the sign is, 0, the y-coordinate is 0. For 1 pi over 6, the coordinate was a half. For 2 pi over 6, the coordinate is root 3 over 2. For 3 pi over 6, that's the vertical, so that's 1. 4 pi over 6 is again root 3 over 2. And 5 pi over 6, we're back down to a half. So those are the numbers that my sequence defines. And I add them up, and I get, let's see, a half plus a half, that's 1, plus 1 is 2. And then I get square root of 3 halves plus square root of 3 halves gives me square root of 3. And so that's the exact value of the second summation. Now we do our last summation. I have an index now of the variable j. My formula is 4 divided by 2 to the j power. That's not multiplication, it's a power. And I'm going to count my index 1 through 5. So I use my formula, 4 over 2 to the index, and my index is 1, 2, 3, 4, 5, based on my starting value of 1, my ending value of 5, so that I can now calculate these terms. I get 2 plus 1 plus a half plus a fourth plus an eighth. So let's see what this is. I get a value of 3, and then I get in halves, 1 half is 4 eighths plus 2 eighths plus 1 eighth, so that's 3 plus 7 eighths. And if I get a common denominator, that's 31 eighths. On this fifth slide, we're going to take advantage of things called closed form solutions. So notice that now my formulas have two variables. I have my index variable, which tells me what I'm counting with, but then in the ending site, the last index value, I also have a variable n. And so this is a formula that says no matter what you put in the top, I have a formula for the sum. So let's see how this is interpreted. If I have the sum, k goes from 1 to 4 of 1, what does that mean? It means I have a sequence of 1s and I'm going to add them. So when k equals 1, I have 1. When k equals 2, I have 1. When k equals 3, I have 1. And when k equals 4, I have 1. So this was when k equals 1. This one was when k equals 2. I have the same thing when k equals 3 and when k equals 4. It's a constant sequence. And so what this is saying is the summation notation says no matter how many n's, no matter what n is, that will tell you how many 1s you have, and when you add them up, you get the value n. So here, my value of n is 4, and that agrees with the formula for what I have. So without doing any summation, without actually listing the values, I know what the answer for the sum k equals 1 to 100. My n is 100, and so the answer is 100. Well, there are other formulas as well. The second one that you need to know is when you're adding the index variable itself. So for example, let's do again n equals 4. K goes from 1 to 4 of k. This is the sequence of k equals 1, k equals 2, k equals 3, and k equals 4. So here I have n equal to 4. And what this formula is telling me is that if you just plug that value 4 into these two locations, so let's see what that predicts for me. If I predict n times n plus 1 over 2 is 4 times 5 over 2, that's 20 over 2 is 10. The closed form says if I add 1 plus 2 plus 3 plus 4, I get that value 10. And we can check the work. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. Okay? So, if I want to ask the question, what is the sum 1 plus 2 plus 3 plus 4, and I keep doing that until I get to the number 30. Well, that's the same as the sum k counts the index from 1 to 30 of k. And so that's exactly this form with n equal to 30. And so the answer is 30 times 31 divided by 2, which is 465, which is a lot faster than adding up those numbers by hand. So I have the same basic pattern. If I have the square of my indices, so that'd be like 1 plus 4. So for example, 1, that's 1 squared, plus 2 squared, plus 3 squared, plus 4 squared, up to, I don't know, 10 squared, which is 100. This is the same as the sum. K goes from 1 to 10 of k squared. And so the formula here, n equals 10, I know what the answer is. It's 10 times 11 times 21 over 6. Now when I'm doing these calculations, I often try to simplify the fractions. So for example, 21 and 6 have a common factor, 3 times 7 and 3 times 2. So I would cancel out the 3. And then I now look at the 10 and the 2. 10 is 5 times 2. So that cancels away the 2. And so what I found is it's the same as doing 5 times 7 times 11, which has a value. 35 times 11 is 385. So if you add the first perfect squares, 1 through 100, 1, 4, 9, 16, 25, 49, 64, 81, and 100, you get the value of 385 without adding them up by hand. And finally, there's this formula for if I'm adding k cubed. This last slide illustrates a number of applications of those closed formulas, but also introduces a few additional observations. So the first example is one that we should recognize. This is the second formula. I have n equals to 10 of the summation of my index k. So the formula is n times n plus 1 over 2 with n equal 10. So I get 10 times 11 over 2, which is 55. If you add 1 through 10, you get the answer 55. The second formula, notice that this does not match the formula in the closed form, because this is not equal to 1. In fact, what it is it says I'm starting at 10. So if I did 10 plus 11 plus 12 up to 20, I can't use my closed formula unless I have the numbers 1 through 9. So let's put them in here. 1 plus 2 plus up to 9. Okay. If I had all of those numbers, I could get the answer. So a common strategy for this problem is, well, let's start by going from 1 to 20, and then let's subtract those first 9 numbers that we know, from 1 to 9. And what that leaves is just the numbers from 10 through 20. Almost forgot the sequence formula. Well, now that I have this, I can use the closed formula for both of the summations. When n is 20, it's 20 times 21 over 2. And when n is 9, it's 9 times 10 over 2. And so I can now calculate those two numbers. I get 210 minus 45. So if I add the numbers 1 through 20, I get 210. And the 9 numbers that weren't there originally give me a value 45. So I get a total of 165. In the third summation, we're going to take advantage of what's sometimes called linearity, or also called the constant multiple and sum rule. When I have a sum of terms, it's as though I do a summation of individual terms, so from 1 to 20 of 2k, and I'm going to subtract the sum from 1 to 20 of the number 1. And so that's the sum rule. So that's the sum rule. And what we'll do is we will also use the constant multiple rule, and this factor of 2, it's 2 times 1 plus 2 times 2 plus 2 times 3. If I factor that out, it's the same as doing 2 times the quantity 1 plus 2 plus 3 up to 20. And we'll subtract the sum of 1. K goes 1 to 20. So I've used the sum rule and the constant multiple rule, and now I'll use the closed formula. The first sum gives me n equals 20, so that's 20 times 21 over 2. And the second summation is a constant 1, and there were 20 terms, so I'll subtract 20. So let's see, what do we get? I get the 2's cancel. 20 times 21 minus 20 gives a grand total of 400. So now we get to do the same thing. This last term, again, I'm going to use a sum. There are 2 terms, so we'll split it into 2 terms. And I also have a constant multiple that I'll factor out the 5 from all those terms. So I have the first term is the sum of k squared, and then I'll subtract 5 times the sum of the k's by themselves. Now, each of these summations has the form of our closed formulas. And k squared, when n equals 8, is n, that's 8, times n plus 1, that's 9, times 2n plus 1, that's 17, divided by 6. And the sum of k, so it's 5, times n times n plus 1, so that's 8 times 9, divided by 2. So again, I'm going to simplify 9 and 6. I'll factor out a 3. 8 and 2 gives me a 4. So it's 12 times 17 minus, again, let's simplify, 8 over 2 is 4. 20 times 8 is 180, which gives me a grand total of 204 minus 180, or a total of 24. That's how summation works. See you in class.